Hello, everyone. Welcome back. We now have a talk from Tyler Gardner from the University of Michigan on probing unique exoplanet regimes with micro-arcsecond astrometry and precision closure phases with CHARA and the VLTI.
Okay.
You have the floor.
Thank you. Hopefully everyone in the room and online can hear me. I'm Tyler Gardner. I'm a PhD candidate at University of Michigan. And first of all, I'd like to thank all the conference organizers for inviting me to give a talk and for putting on a great conference. I'm excited to be here to talk about my PhD research, which has been to try to use long baseline interferometry to probe some unique regimes in exoplanet science. And up here, I have a lot of my collaborators and co-authors on my papers. In particular, I'd like to point out that I work with John Monnier at University of Michigan on this research. Okay, so lucky for me, a lot of the talks in this first morning session have been great introductions to my science as well, so I won't spend too much time retreading old ground, but as we know, there have been now over 5,000 confirmed exoplanets that span a pretty good range in orbital semi-major axis and planet mass, but there are still a lot of gaps in our knowledge of exoplanets, and some of these gaps we can fill with long baseline interferometry. And I'll talk about two such gaps that I'm trying to fill in my PhD research. One is trying to detect planets around intermediate mass stars. So hot stars, or stars that are more massive than the sun, mostly A and B type, spectral type stars on the main sequence. And around these stars, you see a lot of those, almost all of those detections go away. We have some close-in planets detected from transit surveys, and then some wide planets detected from imaging of A-type stars and B-type stars, as we've seen, but really nothing at the AU regime. This is a gap that I'll talk about how we can fill with long baseline interferometry. And another one is for most of these planets, we only have the detection. We actually don't have any measurement of the flux of the planet, which is valuable information for being able to characterize the properties of the planet. And as we saw, for example, in Sylvester LaCour's talk this morning, instruments like gravity and, as I'll show, Micro-Arcs can be valuable tools to be able to characterize planets that are very close into the star, closer in than we can do with classical single dish imaging techniques. Okay, so my talk will be split into these two categories, detection and characterization. And for the first part, I'll focus on the detection. So for these hot stars, A-B type stars of intermediate mass, it's very difficult to detect planets around these with, for example, the radial velocity method, which would usually find a lot of planets in the AU regime. And this is because these stars are rapidly rotating. They have really weak and broad spectral features, so it's hard to do RV surveys to find planets around these stars. But we'd like to fill in this gap to try to see how does planet occurrence rate scale as a function of the mass of your host star, for example. And people have done this in the literature, and results from targeting evolved stars that have spectral features again have shown that there's potentially this 5-fold increase of giant planets at 1 AU for A-type stars compared to solar-type stars. And this is seemingly consistent with direct imaging of wide exoplanets, which also show more massive planets around massive stars. So potentially this gap at 1 AU is filled with exoplanets that are waiting to be detected. So how can we search for them? One way is by using the astrometry method. So this is where we look for the star wobbling due to the gravitational influence of the planet. The problem with this, as many of us know, is that you really need to approach 10 micro-arcsecond level precision to be able to detect Jupiter mass planets around nearby A-type stars. And this is extremely difficult, but with long baseline interferometry, instruments such as Micro-Arcs and gravity have demonstrated this level of precision in differential astrometry of binary stars. So as we saw in some talks earlier this conference and earlier today, if you have a binary star with an interferometer, you can measure very precisely the measurement of the primary relative to your secondary if both stars are within your field of view. And we can measure this down to tens of micro-arcseconds. And then what we can see is this added wobble if there was an additional companion orbiting an individual component of either binary. And in this wobble, we can detect companions down to planetary masses if we can approach 10 micro-arcsecond astrometry. So during the master's portion of my PhD thesis, I took some real binary star data that we had with MERC-X at the CHARA array and simulated what kind of planets could we uncover if we did a dedicated survey of binary stars with instruments like MERC-X or gravity. And what I found is that with the precision we were getting on these instruments, we could detect most planets above 2 Jupiter masses or so on orbits around an AU and greater than an AU, if we can extend the precision we were getting on close binaries to wider binaries. And that would fill this gap really well that I've shown here if we had a dedicated survey to do so. And moreover, beyond planets, this is also a unique regime for finding multiplicity, so stellar components. These will impart much bigger wobbles on the star that they're orbiting. So they're a survey with long baseline interferometry would basically be 100% complete to anything of stellar mass around these stars. And this is another regime that is not very well probed. If you have a massive AB type binary of separation 10 to 100 AU, what is the inner triple rate of these binaries? It's hard to measure, and this is something that we can measure as well with a survey like this. So motivated by the science and the precision we were seeing at these instruments, we started the ARMADA survey, which an arrangement for micro-arcsecond differential astrometry. So it's a survey to detect companions orbiting individual components of binary systems. And for the last 3 years or so, I've been observing with both CHARA and VLTI. We're monitoring 70, mostly A, but also early F and B type binaries. In the north, we use CHARA, the MERC-X instrument. I've observed about once per month from 2018 to 2021, except for COVID months, of course, there was a delay there. And then in the south, we have a large program on VLTI with the gravity instrument, where we use the smaller AT telescopes in service mode for a large survey which spans multiple years to monitor these binary orbits. And you can see that most of there's a peak of the primary star or sample of about an A-type star, and the binary period of the stars that we're targeting vary from tens to hundreds of years in that outer binary orbital period. Okay, so I'd like to show some of our ARMADA results that we have so far, and these include detections of new compact triple systems, as I hinted earlier, a couple substellar candidate detections, and also detection limits for some non-detections. So when we monitor the orbit of an ARMADA binary, what we view is just a small arc of the long period binary orbit. So up there you can see in the orange, we follow this A-type star for about 2 years, and you can see our data spanned a small part of this long period binary orbit. So to fit this outer binary motion, we combine data from the Washington double star catalog to try to constrain this outer binary period. What you can't see at this scale is that there are high residuals to our super high precision MERC-X measurements here. And we can actually search for another period in the system previously unseen to see if there's another Keplerian orbit that we can fit for a triple system. Here we get a nice peak at about 60 days when we do this period search. And then we can fit a triple to this binary star. You can't see it on the scale on the left because we're out at 100 milliarcseconds or so. But if we subtract out the motion of the outer binary, we can see the fit to the leftover wobble, which in this case is now at about 1 to 2 milliarcseconds, which is easily detectable within our error bars with the MERC-X instrument here. Our median residual to this fit is about 25 micro-arcseconds. And this is a newly detected triple stellar companion around the star. So a planet signal would look the same. It would just be a lot smaller. So when we have astrometry data like this, what we can do is detect previously unseen companions, as I've shown, If we have a distance to the system, we can also get the dynamical mass of the system, update the long period binary motion, which is often very poorly constrained since they have long periods. And we can also put some constraints in the mutual inclinations between the newly detected inner orbit and the outer orbit. In the case of triples, sometimes we can actually detect the flux from the newly detected companion. In the case I showed up here, we don't detect the flux, but here's another one, new triple that we found, where in the gray you see we do detect the flux. Now we can see both components going about the center of mass of this newly detected companion. In these cases, we can get individual masses. We can also see which star is it that's wobbling, which star has the newly detected component. If we can't detect the flux, we can also follow them up with RV to see which star it is that's wobbling. And we do have a dedicated RV follow-up from a collaborator at Tennessee State University in the US, using a 2-meter telescope at Faribault Observatory. And this is actually the same object here. So we're able to see in this case that the star that's wobbling is actually the BA component. And this also puts a good second check on the newly detected period that we found in our systems. Okay, so here I wanted to show a subset of a lot of new triple systems that we've discovered with the Armada survey. So here I'm showing the outer long period binary orbits. So you can see, sorry, here we go. You can see, as I pointed out earlier, for some of these binaries, our new high precision Armada data greatly updates the long period orbit, which is poorly constrained with the old, less precise data from the WDS catalog. Also, you can see that we've detected some quadruple systems. So these are systems where we see wobbles from 2 components. Each star itself is wobbling. So it's a superposition of that, the motion that we detect. And in these cases, it happens to be you can actually see the wobble at these large hundreds of milli-arcsecond scales. Though in a lot of these, in most of these new detections that I've shown here, you can't actually see the extra wobble from the newly detected triple on this scale. You have to subtract out the outer binary motion, which I show here. And now we're looking at the newly detected inner wobble motions from either the triple or a quadruple system. Just to point out, at the top row here, we have some three systems here that are shared between Merc-X and gravity. So we can put them to the same, both instruments to the same astrometric scale and see if they're consistent with each other. And for the rest of these systems, half of them are from Merc-X, half of them are from CHARA. And you can see, for instance, in the top left there and the one below it, a lot of these wobbles are now at less than 100 micro-arcseconds, 50 micro-arcseconds in some cases. Though some of them are still a lot bigger because these are all stellar mass components that we've discovered that I'm showing here. And then at the bottom row here, as I was saying, in some of these systems, we've detected the flux from the newly detected triple as well. And then for all of these systems that I've showed, we do have RV follow-up to confirm the newly detected period and also see which star it is that's wobbling, either the A component or the B component of the outer binary. So these RV curves confirm our orbital period as well and make us more confident in the detection. You can see some of them, such as HD 16753, we detected a new long period inner orbit. So we're still following that one, for example, with the RV curve. And just to point out, all of these new triple detections that I've shown today and more are published either in our first Armada paper from 2021 or one that I've recently sent to co-authors and will be submitted soon this year. So keep an eye out for that. And with these new triples, we can do some interesting science. For example, one thing we can do is look at the mutual inclination between the inner and the outer orbits. So it's predicted in triples where the outer binary semi-major is less than 50 AU, which is the case with a lot of our targets, that these systems should be quite well aligned. Most of them have a mutual inclination between the outer and inner orbit less than 20 degrees. And then misalignments of the triples become more common as the binary separation becomes a lot wider. Though there has been some hint that these misalignments tend to increase with stellar mass, and this is in fact what we're seeing. So as I said earlier, we can put constraints on the mutual inclination without full radial velocity information. There's actually two possible values of mutual inclination for all the objects in our sample. Here I've plotted both, either the lower possibility or the higher possibility, except in 3 cases there where we do constrain it. And you can see, save for about 4 that are potentially well aligned, if the lower value is correct in these cases. Most of these seem to be misaligned systems, well over 20 degrees. So our Armada triples so far are seeming to support this claim that there are more misalignments in triples with higher mass primaries for the outer binary. And this tells us something about the environment in which higher mass stars might form. For example, this could support the idea that these companions are forming through disk instability and rapid migration, and kind of having a violent dynamical migration that's leading to more misalignments in these multiple systems for higher mass stars. And I just want to say that for within this next year or so, as our survey is finishing up at VLTI, and we're finishing up some follow-up observations at CHARA, I plan to do a full demographic study of these newly detected inner triples, as well as any low mass companions that we can detect in the future. But I did motivate this talk from a planetary perspective. So I wanted to show so far probably our best 2 candidates for potential substellar detections that we've seen in these binaries. So these both happen to be quite short period binaries, 15 years and only 7 years here. And we can detect, we detect high residuals compared to the air bars, and we can see some periods that are consistent with being able to model an extra wobble motion. Both of them are pretty short period inner companions as well, 13 or 20 days. And you can see now the wobbles here on the right are both at about the 20 or 30 micro-arcsecond level in semi-major axis. So these are candidates right now, no matter which, so these are both A-type stars, and no matter which component it's orbiting, these would be consistent with 50 Jupiter mass objects, so brown dwarf companions. And if we can confirm them, either with more astrometry or with radial velocity, these would be interesting objects because they would lie in the classical brown dwarf desert, where we don't expect to find too many brown dwarfs at short orbital periods. But in cases where we don't actually detect any triples or any candidates, what we can do is see what our upper limits are on planet detections. So these are 4 systems here. We had enough epochs to do our study here. So you can see the top left is quite interesting because there was this candidate detection from RV with a minimum mass of 30 Jupiter masses around this system. But that top curve there is saying that at that orbital period of about 300 days, we could have ruled out 99% of orbits that are above 10 Jupiter masses or so. So we do rule out that planet. And you can see this is consistent with some other objects as well. But at that AU regime, when we have a sufficient number of epochs and good data, we can exclude all stellar mass companions, brown dwarfs, and in some cases, we can start to probe down to the giant planet regime. Okay, so for the last few minutes of my talk, I wanted to switch gears and talk about an effort that I'm involved with at CHARA to characterize exoplanets. So we heard the talk from Sylvester Lecourt using gravity to image, to push the single dish imaging into 50 milliarcseconds or so. I'm going to be talking about trying to find extremely close-in planets, planets extremely close to their star in a different observing mode. In particular, I'll focus on our efforts to try to detect a non-transiting hot Jupiter planet, which is only about 4 milliarcseconds from its star. And if we can develop this method, it could be interesting because Gaia will uncover a lot of planets that can't be characterized with other techniques and other high contrast companions. And if we can show that we can do this one with interferometry, there could be a lot of follow-up objects with Gaia. Okay, so for the Armada project that I've shown so far, we've targeted a binary of about 100 milliarc-second separation with flux ratios about 1:1 to 10:1 or so. So these create a signal in phase with wavelength that's extremely easy to see, tens or more degrees of phase and high SNR. So these are easy to detect, and that's why we can do such good astrometry. But we can also think of a typical hot Jupiter system as an extremely high contrast binary system. The difference now is that for the hot Jupiter systems that we can do, separation is less than 10 milliarc seconds, and the flux ratio is more like 10,000 to 1. And so it creates a signal with phase as well. But if you can see on the label here, now your signal is at the sub-degree level. So in this observing mode, we need to combine many nights of MERC-X CHARA data to try to build up a signal to detect a hot Jupiter planet. Oh, and I should say, we've nicknamed this project Project Prime. And Prime was really, a lot of the pioneering work was with one of John's previous PhD students, Ming Zhou. And he showed it in 2006 to 2010 with some MERC data. They had an upper contrast limit in the H band of a few times 10 to the minus 4, which is getting close to detecting the expected flux from the planet, but not quite there yet. I had a follow-up run in 2019 with the newly updated MERC-X instrument, and we had this really promising detection. So to try to detect the planet, we can fix a lot of the orbital elements that we know from RV and search here in planet semi-major, planet inclination, and also this big omega orbital parameter, which we don't know from the RV. So we find this promising fit here at a contrast of about 2 times 10 to the minus 4, which was extra exciting because it agreed really well with the prediction from RV. And it came from 4 nights in 2019 September. We wanted to follow it up with one more run to increase our confidence in this detection. And we did that in 2021 October with 4 nights. And you can see here that we did, in fact, confirm the position. We also measured a 51-degree big omega value at the same planet semi-major and planet inclination, consistent with the 2019 run. So this was really exciting, and we were about ready to publish this, but we also had MYSTIC K-band data from that run. So in 2021 October, we're now taking data with MYSTIC and MERC-X simultaneously. And so we decided to first search the MYSTIC as well. And unfortunately, we didn't see the planet flux. So this was our expected position. We saw no signal there. So this was unfortunate. I've been spending some time trying to come up with explanations with why we don't detect this planet. One thing that I couldn't get across in this talk is that this observing mode requires a new pipeline, a very intense calibration method to try to get our closure phase precision down to sub-degree level. So one thing that we checked was to make sure it was working. So with this MYSTIC data, John injected the planet straight to the data that we had. And I ran it through my pipeline and tried to see, can we recover these injected planets? You can see from a contrast of 4 times 10 to the minus 4 down to about 2 times 10 to the minus 4. We can still see it. It becomes more marginal at 2 times 10 to the minus 4. But if we had that detection in our chi-squared map that agreed well with the MERC-X data, we would be able to, we would trust it most likely. But unfortunately, we don't even see that. So one other thing we've been trying to see, could the K-band flux actually be lower than the H-band flux for a hot Jupiter? So I've worked with some experts with hot Jupiter modeling at University of Michigan to create updated spectra for this planet, Upsilon Andromeda B, that we've been observing. And so this is showing the model spectra with a clear model and a cloudy model across the H and K band. And the different colors are different phases of the non-transiting hot Jupiter. So the spectrum, the flux changes a bit as the hot Jupiter orbits its star. So our MERC-X tentative detection is around this level here. Agrees somewhat well with the models, but in all models that we've produced so far, the K-band contrast is expected to be better. So we really should detect this thing in the K-band if these models are correct. And so that would include, if we did follow up with these types of objects with gravity, these really close-in hot Jupiter type planets should be great for K-band detections. And so it's kind of a mystery right now why we can't confirm this in K-band, and we're working on it. We submitted a follow-up proposal to get some more MYSTIC data, and we also have a student, Benjamin Sutterholm, who's working on modeling the polarization of the instrument. So if we can have a model of we do see some polarization signal with closure phase as our viewing angle changes. So if we can model this, we might be able to increase our closure phase precision even more and improve our detection. So there's some follow-up work on that. And as I said, if we can develop this method, it could be a valuable tool in the era of Gaia for characterizing close and high contrast companions. And right, so in summary, I'm involved in 2 efforts to try to probe unique exoplanet regimes. One is with Project Armada, where we're trying to detect new planets around A and B type binary systems. And one is Project Prime, where we're trying to directly detect the flux from hot Jupiters. Thank you for listening. With that, I'm happy to take any questions.
There you
go. John Young from University of Cambridge. Could you tell us how the closure phase accuracy you get from VLTI and CHARA compares, and if you know anything about what limits it?
So I haven't done for the Project Prime, where we're really trying to get precision closure phases, I haven't done any work with gravity yet. Gravity, we focused on the binary stars where it's easy to detect the stars. So I don't know so much the closure phase precision from there. For Merc-X, to detect these planets, we have to get down to sub-degree closure phases. And we are indeed doing that with both Merc-X and Mystic. So to do it though, there's a whole calibration method that we have to do where we look at how we model closure phase across things like hour angle, azimuth, altitude of the object, and we try to build up a model to then apply to our data. And because you do see some drifts with these parameters, and so a lot of my calibration methods for Upside Andromeda B are trying to model these out. Currently, when we model them out, we can get down to sub-degree, but it's challenging. These are mini nights. We're on the target basically all night, and we're combining multiple nights of data each time. So, and these are bright objects, these hot Jupiters. So for bright objects, it's getting quite good. Yeah.
Thank you.
At the back.
Denis Defer, KU11. I have a question regarding the K-band non-detection. Do you resolve, because it's so close, do you resolve also this planet with all baselines at K-band?
Yes, yeah, we should still resolve it. The resolution limit in H-band is 0.5 milliarcsecond. We're using the longest baselines at CHARA with I don't know it off the top of my head with K, but it's less than 4.5 for sure, which is where this planet is.
Yeah, but I meant with all baselines of Merc-X, or only the longest baseline that you resolved?
I think we resolve it on all baselines. It's definitely true that the longest baselines are most valuable for us, but we do always have the longest baselines in the data that I've shown. So,
okay.
Yeah.
Thank you.
Any more questions? I believe we have time for one more, if there's one more. Okay, well, thank you very much. Very nice talk.
Thank you.